In the previous video, we calculated a slope to describe the relationship between the size of a house in square feet and the price of a house. So that value that we calculated, is that a statistic or a parameter? So anytime we're calculating a value from the sample data, that's going to be a statistic, right? This is just based on the sample. We don't know what the true relationship is like in the population. So when we see a statistic, obviously the slope here is not zero. So it does seem like there's some relationship between size and price, but we always have to ask ourselves, could it be due to chance alone? Right? We want to rule out that just by chance explanation before we say anything too strong about the relationship. So let's start by stating our hypotheses. So we're not going to use B here because B is for the sample slope. We need a different symbol to represent the population slope, so we're going to use beta for that. And just kind of in general, we'll mostly use Greek letters when we're talking about parameters and regular letters when we're talking about statistics. So beta here, this is the population slope. And our null hypothesis is that there's no relationship between size and price. So beta would be equal to 0 if there's just a flat regression line. It doesn't matter what you plug in for size, your predicted price is the same either way. Or if we wanted to write that in words, we could say that there is no association. So this is no association between size and price. That's our explanatory and response. And we're talking about in the population, right? Because this is a parameter, so we know that there's a relationship in the sample, but we're asking whether it's possible that there's no association in the population. The alternative hypothesis, technically it could be one-sided or two-sided, but this one just says, is there a linear association? So it doesn't seem to presuppose that it's going to be positive or negative, so we'll just say not equal to 0. And this is the more common one. This is the default in JUMP anyway. So the alternative hypothesis is that there is an association, and again, between size and price. I'm going to be lazy and not write it out. So earlier in the class, we've carried out simulation-based inference by writing all of our responses onto cards and then dealing them out into groups to match the explanatory variable. But that doesn't really make sense here because we don't have any groups. It's not like there's treatment or control. So what do you think we should do? How could we modify the simulation that we've been using to make it work for this scenario? And when we do that, when we have our simulated sample, what statistic could we use to summarize that sample? So pause the video here and think about how you would design the simulation. So we're still going to start off the same way. We're going to write our response variable on cards. So in this case, that would be the prices, right? The prices on cards, and shuffle everything together. But then instead of dealing the response variable out into piles, into groups, instead you're going to randomly match it up with sizes. So then randomly pair up the prices that we have here. Randomly pair up prices with sizes. So instead of dealing out into groups, which would represent a categorical explanatory, we're going to deal them out into the sizes that we have in our sample to represent the quantitative explanatory variable. And as we do this, obviously if we're just randomly pairing them up, there's not going to be any association between size and price, right? Because we're just randomly matching them. So as we do this, the goal is to represent no association between the variables. So we want to know what values could we get if there were really no association between size and price. And then we need to calculate something as a way to summarize the sample, and there's a couple different options for us. I'm going to go with the slope. I'm just going to calculate the slope for each sample, but you could also consider doing the correlation, R, or the R squared. Any of those would be appropriate ways to measure the strength of association in the simulated sample. And then we're going to repeat lots of times. So we're going back to the Rossmann chance applets. This time we're going to do the one that says analyzing two quantitative variables. And I'm going to clear this out and copy paste in my data. When I copy paste from JUMP, a lot of times the headings get lost, so I'm going to add those in. Square feet was the explanatory and price was the response. And I'll click Use Data. And I can see if I show the regression line, this is the same one that we saw in a previous video. So then for my shuffle options, I do need to choose a statistic, and notice there's options here, the ones we talked about, and a few others too, a T statistic, F statistic. We haven't talked about that yet, but that's another way to summarize the sample. Let's just use the slope for now. And I'm going to do it with data first, so I'm going to shuffle my Y values. And you'll notice that these are all the same values of square foot and price that you have in the other list, but they're randomly matched up. So if we look at the plot for this one, this came out a little bit positive, but seems like not as positive as the original data. So the slope, which is recorded, is being put into that third graph. So this is the shuffled slope. If we do it again, this time when we randomly matched up the sizes and prices, we ended up with a little bit of a negative relationship. So that negative slope is showing up in the graph. By the way, that gray line, that's showing the previous shuffle, so it's kind of keeping track of the shuffles and the slopes that way. This time still negative, but a little less so than before, a little closer to 0. So that's showing up there. And we can do a whole bunch of those. Let's do 997 more. That worked out pretty good. It didn't seem to take too long. Let's do 9,000 more, see if I'm tempting fate. Okay, that almost crashed it, so maybe don't do that. Okay, so let's think about what we're seeing in this graph. So if we think about what this histogram represents, these are all the values of the slope, right? Each one is a slope from a different simulated sample. And specifically, this represents the values of the slope when there's no association. Right? We assumed no association as we carried out our simulation because we were just randomly matching up sizes and prices. In other words, this is the values of the slope that you would get if the null hypothesis were actually true. So how likely would it be to get our sample slope, the real sample slope, if the null hypothesis were true? To see that, we're going to find 212. That's the slope from our sample. Here's 212. And see how likely it is to get that value or more extreme. But actually we want to look on both sides because this is a two-sided test. We've got not equal in our alternative. So we're going to count the values 212 or more extreme and also include the negatives. So to do that in the applet, we'll put in 212.74 and then we'll change this to beyond. And we'll count those. And out of 10,000 shuffles, we had 117 that were 212 or greater, or 212 or beyond. So it looks like this happens about 1% of the time that we would get a slope this extreme just by chance. So pretty unlikely to get a value like this. So to get our p-value, we used the applet, and we had done 10,000 shuffles, which was a big mistake because the applet almost couldn't handle it. 117 of them were that extreme, which gave us a p-value of 0.0117. And in context, this means that we have strong evidence, right? We've got strong evidence of an association. And that's an association between size and price, and we're talking about in the population. So it doesn't seem like this is the kind of association that we would see just by random chance. It seems like there must be a genuine trend in the population.